So, have you ever wondered how we create materials with perfectly tuned properties? Like the super strong steel in a skyscraper or the solder that holds your phone together? Well, behind almost every single one of those advanced materials, there's a hidden map, a secret recipe book that engineers use to, well, build our world. Today, we're going to pull back the curtain and learn how to read one of those maps.
Let's start with a really simple question that I bet you already know the answer to. Say you're making a drink, coffee, tea, whatever. How much sugar can you actually stir in before it just stops dissolving and sinks to the bottom? There's a limit, right? You've seen it happen. Well, that limit has a scientific name. It's called the solubility limit. For sugar and water at room temperature, it's about 65% by weight. If you're below that, you get a single uniform liquid we just call syrup. But the moment you try to add more, you get a mixture of that syrup and solid sugar crystals. You've just created what's called a two-phase system. Now, that's simple enough for sugar and water. But what if you're mixing molten lead and tin to make solder, or iron and carbon to make steel? Suddenly the stakes are a whole lot higher, and the way they interact is way more complex. For that, engineers need a much, much more powerful map. And this is where the phase diagram comes in. I want you to think of it as the ultimate recipe map for material scientists. It tells them exactly what they're going to get at any combination of temperature and composition. So this is a phase diagram for a lead-tin alloy, the classic ingredient for solder. And yeah, at first glance, it might look a little intimidating, but it's just a map. And like any good map, once you know how to read the symbols, it can tell you exactly where you are and where you're going. The layout is actually pretty straightforward. The vertical y-axis, that's your temperature. The horizontal x-axis shows the composition, in this case, how much tin is in the mix. And all those labeled regions on the map, they represent the state or phase the alloy will be in. L is easy, that's for liquid, and those Greek letters, alpha and beta, they just represent two different kinds of solid phases.
Okay, now let's look at one of the most important features on this map. See, this is a special kind of map called a eutectic system, and it has this incredibly useful landmark you need to know about. It's called the eutectic point. You can think of this as the magic mixture. It's the one specific composition that melts and solidifies at the lowest possible temperature for the entire system. It's a real sweet spot. For our lead-tin alloy, that eutectic point is at exactly 61.9% tin and 183 degrees Celsius. And right at this precise spot on the map, something amazing happens. The liquid doesn't just slowly turn into one solid, then another. No, it transforms instantly from a single liquid into a super fine mixture of two solid phases, alpha and beta, all at once. It's a really unique transformation. So the single-phase regions are easy enough to understand, right? Liquid's liquid, alpha's alpha. But what's the deal with that big area at the bottom labeled alpha plus beta? We know both solid phases are there together, but how much of each? Is it a 50-50 split? 90-10? How do we know? Well, guess what? Our map has a tool for that. It's a simple but really powerful calculation called the lever rule, and it lets us figure out the exact proportions with total precision. Let's just try it out. Let's say we have an alloy that's 40% tin, and we cool it down to 150 degrees. We find that exact point on our map right there in the alpha plus beta region. Now, to use the lever rule, the first thing we do is draw a horizontal line. It's called a tie line, straight across that region at that temperature. The rule works just like a seesaw. Seriously. Think of our overall composition as the fulcrum, or the pivot point. The lengths of the lever arms on either side tell us the fraction of each phase. So to find the fraction of phase alpha, the stuff on the left, we take the length of the opposite lever arm and divide it by the total length of the tie line. All right, let's just plug in the numbers from our map. The left end of our tie line, C alpha, is at 11% tin. The right end, C beta, is at 99%. And our overall composition, C0, is 40%. So the fraction of alpha is 99 minus 40 divided by 99 minus 11. Punch that into a calculator and you get 0.67. So at this exact spot, our alloy is 67% solid alpha and 33% solid beta. The map told us the answer. Okay, so we can read the map and we can do the math. That's cool. But here's where it gets truly amazing, where this whole thing just comes to life. This abstract map doesn't just predict numbers, it predicts what the material actually looks like under a microscope.
This is the crucial point, the thing you really have to get. Every single point, every line, every region on this diagram corresponds to a real physical microstructure. The map on the page is a direct blueprint for the structure of the material on the microscopic level. And here is that connection made real. On the left, that special eutectic point from our map. On the right, that's the structure it creates. Because those two solid phases form at the exact same time from the liquid, they grow together into this beautiful alternating striped pattern. It's called a lamellar structure. Now, let's move to a different point on the map and see what happens. If we use a composition to the left of that eutectic point, it's called hypoeutectic. The map predicts that as it cools, solid chunks of the alpha phase will form first. Then, when the rest of the liquid hits that eutectic temperature, it solidifies into that straight structure around the initial alpha chunks. And look at the micrograph. That's exactly what we see. The dark spots are that first alpha phase surrounded by the eutectic matrix. The map predicted it perfectly. Okay, now let's take this whole concept and apply it to, well, arguably the single most important material in human history, steel. And here it is. This is the phase diagram for iron and carbon. I know, it looks way more complicated, but it works on the exact same principles we just learned. This one chart is the foundational blueprint for creating everything from the cast iron in your cookware to the high-strength steel in a bridge. In steel, there's a point that's really similar to the eutectic point, but with a twist. It's where one solid phase transforms into two different solid phases. We call this the eutectoid point. The structure it creates is called perlite, and it's this layered mixture of a soft phase called ferrite and a very hard, brittle phase called cementite. And here's what that perlite looks like up close. Those super fine alternating layers of soft ferrite and hard cementite, they act like a natural composite material on a microscopic scale. This unique structure is precisely what gives so many common steels their signature combination of strength and toughness. It's an incredible design. So, what's the big takeaway here? Why does all this matter? Well, phase diagrams are not just some academic charts in a textbook. They are predictive, powerful tools. They are the recipes that allow engineers to design materials from the atoms up, targeting specific properties like strength or hardness or a certain melting point. From the tiny bit of solder joining circuits in your laptop to the massive I-beams holding up skyscrapers, these maps, they are the invisible foundation of our entire modern world. Which really leaves us with a final thought, doesn't it? If this one map is the blueprint for a material as vital as steel, just imagine what other hidden maps are out there, defining the plastics, the ceramics, and the polymers that shape the rest of our world. Thanks for watching.